Hi, ladies. Here is our 7th day of doing this distance learning from home. It's April 6th, 2020, and we are getting ready to start Chapter 4. So our outline for today includes prayer, quite a few updates. There's no prime time, some class content, what your homework is, and looking ahead. So today I want to start off by doing the prayer of St. Thomas Aquinas, which is actually the prayer that they use at Lake Catholic every day. So if you join me in the name of the Father, the Son, and the Holy Spirit, amen. Grant me, O Lord my God, a mind to know you, a heart to seek you, wisdom to find you, conduct pleasing to you, faithful perseverance in waiting for you, and a hope of finally embracing you. Amen. In the name of the Father, and the Son, and the Holy Spirit, amen. So I've started a Google Doc for you to write prayer requests and special intentions. You are welcome to put your name by it or not. It's your choice. The link is here. I'm also sharing it in the email for the outline. So feel free to add any prayer requests that you want to either just have us praying for, or if you want me to add them here to the email or the PowerPoint at the beginning of class, that is fine too. So updates. The tests online went really well from my perspective. It looked like everybody got in, everybody took the quiz, everybody had no issues with their time. It was interesting to look at some of the answers. There's a couple of things that I wanted to clear up. One of those is that about air. I had a number of different answers about air, but air is a mixture of gases. It has oxygen as well as like carbon dioxide that we exhale, and there's also a lot of nitrogen gas in it, along with lots of trace amounts of other things. So air is not just oxygen. It has a number of different gases. So it's a mixture. It's homogeneous. Typically, we think of what we breathe as pretty much homogeneous. There are differences depending on the elevation and whether you have pollution and things like that. But for what we're doing, it's truly a homogeneous mixture of gases. The other thing that I noticed is it was fairly commonly answered about density. So density is intensive. It doesn't depend on the amount of material present. And that's because it's mass divided by volume. So even though mass is extensive, volume is extensive, density itself is not extensive. And the best example that we've already talked about is that the density of water is always 1 gram per mil, regardless of how much you have. So you can have a teaspoon, you can have a cup, you can have a gallon, and the density is always 1. So 2 things that were commonly missed that I wanted to clarify today. So all the rest of the grading is in progress. I am still working on the rest of the tests, the 2 sections, your 1-pagers as well as your photo document. And I also wanted to state I've graded all your lab reports, given you guys comments back, but I wanted to say, in light of the fact that it doesn't look like we are going to get back together and have much time to do any labs if we do get back together in May, I'm going to say don't revise the current lab report or do the second one, but I would appreciate it if you would at least look at the comments that I made. So I want to talk about Kami, and I'm going to talk about that in a little bit when I have my internet Chrome open. And the other thing that I want to talk about was future schooling. So there were some new guidelines sent out before the weekend regarding what we should be doing with classes and how things are going to be going in the future. And we all realize that there are other states that are stopping online schooling, and I don't know what is going to happen as we move forward over the course of the next number of weeks. With spring break next week, by the time spring break is over, the whole situation may change again, because it does seem to be changing very frequently. So I've spent a lot of time over this past weekend fretting, worrying. My family could attest to the fact that I've been a real pain, because I've been trying to think about how to deal with this class and what do I want to do and what's important. And so I spent a lot of time really considering this. And I kind of boils down to what I told you back at the beginning of the year, that the goal of this whole class is to help prepare you for next year. And there are a lot of things that needed to happen throughout the course of the year in order to prepare you guys for your junior year of chemistry. We had to transition out of biology. We had to go into a physical science. We had to take notes from a physical science textbook. We had to do things that were very different from what we were doing in biology. And it takes a while to get used to all of that. Part of the goal is to introduce you to some concepts in chemistry that kind of help build the foundation, which is kind of where we are now. But in addition, I've learned from the 3 teachers who've taught the junior year chemistry at Beaumont that there are certain things that if I cover them, they really help you guys in your junior year. One of those is unit conversions, and we've already spent quite a bit of time on that, and there's always work that can continue to be done on that, and I'm going to put some videos out there for that. But the other 2 things is some naming of compounds. How do we name them? And the other thing is balancing equations. And both of those concepts we haven't gotten to yet, and it's because we haven't talked about atoms and elements yet, and that's kind of what we're getting ready to start here. So I wanted to tell you personally that regardless of what happens as far as school and Beaumont or the state, how far it goes, is that my intention is to continue posting videos and information in order to help you be successful next year by introducing those concepts to you. In order to get through the material before the end of the school year, assuming we're still on until the end of May, it's going to look very different than it has in the past. I'm not going to be covering everything that's in the textbook. I'm not going to be doing every activity and everything that I would have done if we were together in class. I'm going to be deleting some sections. I'm going to be modifying some other things. But for the most part, I can get through the material and get you at least introduced to naming, introduced to balancing, because those are the things that are going to be really helpful to you next year. It's very well known that Mrs. Iskander and Mrs. Hamrick are going to have to go over those again next year. They did this year, and that's okay. But the fact that the students who are currently JUICE earners had an opportunity to do those things with me, practice them some, then they came back and they did them again in the fall. They were better at them than they were with me, and that just helped them be more successful. And a number of students who come back and talk to me sometime during their junior year say that those are the things that were the most important for me to get to. So I am still prepared to do that, and that's going to be going regardless. So regardless of what happens, I will continue posting videos out onto Edpuzzle, as well as putting things on P-Learning, regardless of what's happening as far as school goes. The other thing is packets and mailing. I had a number of students send me their address, so thank you very much. I had all that stuff ready to go, and then I got an email near the end of the day on Friday. Made me stop and think maybe that's not what I should send out, and I'm kind of glad that I didn't, because I've decided that I'm going to send everything out at the same time. With all the others, with so many states saying that the kids are home until the end of the school year, we may be that way too. And it's kind of expensive to mail all this stuff out, and I figure I'm just going to mail once. So I'll be getting those things out and together probably at the very beginning of our spring break, because it'll take me a while to copy the last couple of packets for the other chapters and the handouts that I would normally hand out. So that'll be going to you guys. And if you did not send me your email or send me your street address and you do need me to print those stuff out for you, please let me know. So today we're going to be starting some stuff in chapter 4. Oh, but first, personal update. So here are some pictures from our trip to Palau. So we spent part of one morning doing a land tour on one of the islands, and it was called Peleliu. And this was an island that the Japanese had invaded during the war, and the Americans came later to take the land back. And here are some things that are left from when the Japanese were there. So here is a Japanese tank. It's quite rusted. There's some bullets and bullet holes in the walls here. Here is one of their large guns, a 200 millimeter gun. This was their fuel storage bunker. This was one of their buildings, and you can kind of see it's like the jungle has taken it over. This other picture here is the other 200 millimeter gun. This was their headquarters building, and it was 2 stories. It had, well, now it has a sunroof, but there's this rebar that was there in the building, and it really, it's amazing how well it was built. It was really built to last, because while some of it has crumbled, I mean, you can see here that the framework is still there. There's windows and framework here. And this is a Quonset hut that's still intact. And I didn't really know what a Quonset hut looked like. And so seeing this here was quite kind of interesting to me. So this was some of the things that were left over from the Japanese when they were there and had the island. And next time I've got some scrapbook pages to show you for a couple of the other things where the Japanese were during this time. Okay, so chapter 4. We're going to be working on all of these topics. Today, I'm going to kind of focus on chemical formulas and a little bit of atomic theory. I'm not going to get through everything of that today, but we're going to start it. So chapter 4, green packet, we have a couple of worksheets that we're going to be using, and I highlighted those in the email that I sent out on Sunday evening. So the first thing is we're going to watch a short video, and there is a worksheet that has some questions on here, and it's a document, so you're welcome to type in the document or write on a sheet of paper, whatever you prefer. It does not matter to me how you do that. So here is this one. Here it is. So this is ancient chemistry video questions. So we're going to go ahead and watch this video about ancient chemistry.
Let's put down the chemistry textbook for just a second and grab the history book. Which ancient civilizations are you learning about? Egypt, China, Rome? All of the ancient civilizations we still talk about today have at least one thing in common. They harness the awesome power of chemistry. Let's begin in the Stone Age. For thousands of years, early humans wandered the earth, using stone tools and weapons. They grabbed what food they could find and huddled together for warmth. Then our ancestors discovered a very, very important result of certain chemical reactions: fire. Fire was great. You could cook food over it, you could keep warm, you could stay awake later plotting hunting strategies thanks to the light it provides, and you could keep hungry predators at bay. But early civilizations figured out one of fire's finest features. You could use it to make stuff out of other stuff. As early as 6,000 years ago, Egyptians used copper to make tools. They figured out that if they exposed copper ores to fire, they could extract the precious metal and pour it into molds. Archaeologists found copper pins, chisels, needles, and other artifacts all over Egypt. Egyptians were also known for their colorful paint. That famous Egyptian blue is believed to be the first synthetic pigment, dating back to 3000 BC. Using crushed natural chemicals, or mineral salts, ancient Egyptian painters created vibrant murals in the tombs of the pharaohs. The next big technological leap was the discovery of alloys. About 4,000 years ago, curious African and Asian folks figured out that with the help of flame, you could take this copper stuff and combine it with this tin stuff to make stately bronze. People usually think of gunpowder and fireworks when they think of ancient Chinese chemistry. But thousands of years before those inventions, Chinese were the emperors of bronze. Ancient China produced thousands and thousands of bronze objects they used in rituals. Plates, cups, bowls, and other vessels were used for offerings to ancestry at family temples and for burial rites. It took a lot longer for ancient chemists to figure out iron. Turning iron ore into something useful was a much more complicated process than making bronze. But with the help of fire, iron production and smelting began around 1200 BC in the Middle East, and it took another few hundred years to spread to Europe and China. But the true masters of iron were in India. By about 300 BC, India was making steel, something Europeans didn't figure out for centuries. The Indian fusion of iron and carbon made swords of so-called wootz steel that were resilient, sharp, and strong. Today, there are refined production techniques for making all sorts of steel, but the swords of Damascus steel were extraordinary for their time. 2,300 years later, scientists still can't replicate the technique for making the razor-sharp blades. It's important to mention that ancient civilizations weren't just big doers, they were also big thinkers. While the Indians were mastering steel, philosophers in ancient Greece, like Democritus and Aristotle, started asking questions of how nature is put together. Many consider Democritus to be the father of modern science. Democritus and his mentor Leucippus developed the idea that everything is made of atoms, an infinite number of indestructible units of all shapes and sizes that have always been, and always will be, in motion. Some modern historians and scientists say Democritus simply got lucky, and recent evidence just happens to confirm his hypothesis. But the Greeks weren't that thrilled with Democritus either. Rumor has it that Plato, another thinker of the time, wanted all of Democritus's works burned. Plato thought Democritus was too materialistic, that ideas ruled the universe. Democritus and Plato, the Hamilton and Jefferson of their day. But like some sparring heads of state, parts of both their ideas contributed to the formation of science. Though, after several centuries, it turns out Democritus was more correct with his atomic theory. Now, Aristotle, a student of Plato, meanwhile wrote one of the foundational texts of Western science and philosophy. It was called Physics, but it was really just about nature and the world around Aristotle. He believed everything on the planet was made up of 4 elements: earth, air, fire, and water. He also thought the heavens were made of a weightless substance called ether. This philosophy was extremely influential and dominated science until the European Renaissance in the 1500s. Proof that you don't have to physically make something to be hugely influential in the study that became known as chemistry. Now let's talk about one of the most Hollywood-loved ancient civilizations, the Romans. Sure, from a chemistry perspective, the Romans were big time. They invented coinage of all kinds, thanks to Greek knowledge, concrete and cement, to name a few. But their biggest chemistry conquest? Plumbing. Specifically, indoor plumbing. The Romans crafted pipes out of lead metal, which doesn't occur naturally on its own, so you really have to know your chemistry to extract it from rocks, and the Romans did. They were also the first to seal pipes in concrete to help deal with water pressure and bursting pipes. All of these accomplishments happened over about 4,500 years, a mere blip on the evolutionary radar. From melting copper pins to crafting lead pipes, the civilizations we still talk about thousands of years later left their mark with metal. And those metals were forged, formed, and reshaped with chemistry.
Okay, so hopefully you were able to get the answers to the questions here. So that's kind of where our story of chemistry and atomic theory begins. And the first individual that gentleman talked about was Democritus, who is considered the father of modern science. So the next piece of this is something that you read in your textbook in 4.3. And this is also on page 7 of the green packet, and we'll talk about that later on after I get the copies that are being mailed or delivered to your classmates. With those of you who can print it out, you can already take a look at it. So there were 5 parts, and they were listed in your book. Dalton actually expanded Democritus's ideas. He said elements are made of tiny particles called atoms. Atoms of any given element are identical. Atoms of a given element are different from those of other elements. Elements or atoms of one element can combine with atoms of other elements to form compounds. A given compound always has the same relative number and types of atoms. So water is H2O, and it's always H2O. It's not anything else. And atoms are indivisible in a chemical process. We don't break apart the atoms. They're not created, they're not destroyed. A chemical reaction simply changes the way atoms are grouped together. So those were Dalton's contributions to our understanding of atomic theory. So the next person on this journey is going to be Ernest Rutherford, who we're going to talk about. He is in your textbook in a couple of sections. Again, there is an article or a paper here with some questions for you to answer. So you do want to have this handy as you're watching the video and listening to it, because you're probably going to need to pause the video as the gentleman is talking in order to write down some of these answers. So here is a video about Ernest Rutherford.
Thanks to electron microscopes and similar technology, we can see individual atoms. But it wasn't that long ago that scientists knew very little about these basic units of matter. Ernest Rutherford carried out several ingenious experiments in the early 20th century that helped create nuclear science and move forward into the modern age. Rutherford grew up in New Zealand. He was so smart, Gandalf himself sent him to Cambridge University to do research after college. Actually, Rutherford just got a real-world scholarship, but he was really smart. He went to work for a scientist named J.J. Thomson, who later won a Nobel Prize for discovering the electron. Thomson had a theory about atoms called the plum pudding model, but just hang on to that idea for now. We'll come back to it. Rutherford liked to take on the gnarliest problems of physics, and he devised experiments to learn more about radiation. He discovered and named its 3 different types: alpha, beta, and gamma. Rutherford was a top-tier experimentalist. He worked with alpha radiation for 9 years before he had enough useful data to declare its particles were positively charged. Rutherford had a hunch that these alpha particles were a form of helium atoms, but he needed more proof. We'll come back to that, and also the plum pudding, I promise. A better understanding of radiation led Rutherford to discover nuclear decay. When an element like, say, thorium produces radiation, it can become a whole new element. Since radiation is particles escaping from the nucleus, if the number of protons in that nucleus change, then the product is a new element. Rutherford now wanted to use radiation to learn more about atoms themselves. So he moved back to England, this time to the University of Manchester. There, he started working with a young researcher named Hans Geiger. Yes, the same one the counter is named after. Fun fact, the counter actually came about from an experiment that Rutherford invented. Anyway, by 1908, Rutherford was able to prove that alpha particles produce the same light spectrum as helium. See, light spectra are like fingerprints for the elements, so alpha particles and helium matched, confirming his hypothesis. That same year, Rutherford won a Nobel Prize for his work in radiation. But of course, he wasn't done. He sent Geiger and a younger student named Ernest Marsden to work with an alpha particle again. His group designed an experiment where they launched alpha particles at a thin piece of gold foil. A circular screen around the setup would show a glowing point where alpha particles struck it. The alpha particles seemed to pass right through the gold foil, striking the screen on the opposite side. But Rutherford had a hunch. He told Marsden and Geiger to keep an eye out for alpha particles hitting other parts of the screen. Sure enough, they soon observed a few particles that were apparently bouncing backwards off the foil. Rutherford's recollection of the discovery is famous. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you, he said. The gold foil experiment led Rutherford to his own model of the atom, one that effectively launched modern nuclear science. And now we talk plum pudding. Rutherford's mentor, J.J. Thomson, described an atom that was mostly positively charged with some negative bits scattered throughout, much like raisins in a plum pudding. Appetizing, right? Instead, Rutherford envisioned an atom that was mostly empty space, with a positive charge concentrated just in the nucleus and electrons orbiting around it. Most of the positive alpha particles simply passed through, but when they struck that nucleus, the positive charges repelled each other. That action sent some of the particles bouncing back towards their source. This is what makes Rutherford a great experimentalist. He let questions, curiosity, and intuition guide his experiments, and then he built a theory when he had enough rigorous proof to support it. But like plum pudding leftovers, Rutherford's atomic model was short-lived. In 1912, a student named Niels Bohr joined his lab. Bohr himself would soon elucidate the structure of atoms, including discrete orbitals where electrons tend to exist. The Bohr model overthrew Rutherford's and lives on with minor adjustments to this day. Rutherford is remembered for the experiments that kicked off atomic science and as a mentor to some of the greatest chemists and physicists of the 20th century.
So Rutherford's experiment with the gold foil is famous, and the whole idea here is to understand what happens with charges. So all of you are familiar with the fact that when you have a positive and a negative charge, they're going to be attracted to each other. If you have a positive and a positive, they're going to repel each other, just like magnets, just like other charges that you've talked about in the past. So what he's saying here is that the only reason these positive charges would bounce back is that they had to hit something that was a positive charge. So by finding a few of them bouncing back here, that made Rutherford believe that there had to be some concentrated positive charges in there in order for these things to bounce back. This very thin gold foil was so thin that it was essentially one atom thick. So there was not a whole lot of atoms here for it to run into. So his idea is very important, but it was also a very ingenious experiment that he had the students in his lab do. So now that you've filled those out, the next time I'm going to show a similar video about Niels Bohr, and that's going to be the model that you might already be familiar with that has electrons in orbitals. So regarding all of this and how much do you need to know and how much of it is vitally important for you for what we're doing now, typically I would say you end up with a multiple choice question on a test that you're supposed to be able to indicate what did Democritus contribute, what did Ernest Rutherford contribute, what did Dalton contribute. We'll also talk about Niels Bohr. However, I think at this point in time, that's not going to be happening. However, I think all of these individual contributions are important, and I have been told by other students at times that there have been readings on standardized testing about like Ernest Rutherford and John Dalton, so you might see them again. It's a good idea to be familiar with them. But I don't expect you to memorize all of this and who did what at this point in time. So Switching topics, 100%. I want to talk about chemical formulas, and this is important for us to get onto later on, where we're going to talk about how to balance equations. But first, we have to talk about chemical formulas. And some of these things you've seen. You've seen things like H2O, which is water, and that tells you that there are 2 atoms of hydrogen and 1 atom of oxygen, and they're bonded together, and that's what water is. You've seen CO, carbon monoxide, 1 atom of carbon, 1 atom of oxygen. Carbon dioxide, 1 atom of carbon, 2 atoms of oxygen. H2, which tells you that there are 2 atoms of hydrogen. But what about some of these other things? We've got CuSO4. Remember, Cu is a symbol for copper. So there is 1 copper atom, there is 1 sulfur atom, and there are 4 oxygens. Magnesium bromide, we've got 1 magnesium and 2 bromine. Let's talk about coefficients, because we're going to run into these as we go through, but we still need to know and count how many atoms there are. So coefficients are very much like what you see in math. So 3x means that there are 3 x's, or x plus x plus x. In this case, the 3 in front of B2O3 means that there are 3 of these molecules that contain 2 borons and 3 oxygens. So in total, when we want to figure out how many borons we have 3 times 2, which gives us 6. And oxygens, we have 3 times 3, which gives us 9. So let's look at a few more of these and practice. So 2H2SO4 means that there's 2 H2SO4 molecules. That means H2SO4 and another H2SO4. So we can count them. There's 2 hydrogens here, 2 hydrogens here. That means that there's a total of 4. There's 1 sulfur here, 1 sulfur here, which is a total of 2. And there are 4 oxygens and 4 oxygens, which give us a total of 8. Or you can look at the coefficient and multiply it by the subscript. 2 times 2 here is 4. 2 times the 1 that's implied by the sulfur is 2. 2 times 4 is 8. So another example, 4C4H10 means that there are 4 C4H10 molecules. Again, you can add them all up. So carbon, there's 4 plus 4 plus 4 plus 4, which is 16. And hydrogens, there's 10 plus 10 plus 10 plus 10, which is 40. Or you can multiply the coefficient by the subscript. 4 times 4 is 16. 4 times 10 is 40. So that's coefficients. So now there's one more piece for writing chemical formulas. Sometimes we need to write them with parentheses in there. Parentheses always have a subscript at the end of the parentheses. So here we have Al2, parentheses, SO4, closing the parentheses with a 3. So this means that there are 3 SO4s bonded to 2 aluminums. So what we end up having is 2 aluminums. There are 3 sulfurs, and then there are 4 times 3 oxygens, which are 12. Another example is the parentheses NH4, close the parentheses 2, times SO4, which means that there's 2 NH4s that are bonded to SO4. So with this, we have 2 nitrogens, 8 hydrogens, 1 sulfur, and 4 oxygens. You can have a coefficient in front of a formula that looks like this, so you're actually going to be combining the last slide where I talked about coefficients as well as the parentheses. So what I'm going to have you do is do some practice here. So this sheet would be practice in your green packet, page 9. I've put it on P-Learning as a PDF. That's the only way I have it. I can't convert it to a doc because it's copy protected. So in here, you're going to go through and write down how many atoms there are of each of the elements that are in any of these molecules. You've got some parentheses here. You've got some coefficients here. You've got some parentheses and coefficients. You've got a few molecules that have 4 atoms in here. So you're going to want to count all of those carefully. So that is actually going to be your homework. If you want to just do it right now while you're thinking about it, just pause the video and go ahead and work on this right now. Actually, I wanted to tell you about Kami. So if you don't have a way of printing things out, there is a free add-on to Chrome that allows you to write on PDFs. So I'm going to open this document from my computer. So this is what it would look like. So you can use this free version of Kami that allows you to actually write on here. So if you want to type, you could actually put a text box here and say that there's 1 here and there's 1 here. And you can basically fill in the PDF here. Afterwards, you can save it, and then you can go ahead and save it to your Google Drive and submit it that way. This may be the easiest way to work on some PDFs and allow you to do this even if you are unable to print out. There are some things, like some of those coloring pages that we've done in the past, that are not going to be very conducive to this, but you might find that it works. So Kami, it is K-A-M-I, is a free add-on to Chrome in the Google Store. So you want to be using Chrome in order to have this work. But I haven't used it a ton, but it seems to be pretty intuitive and user-friendly for what I have worked with it. So go ahead and try it and work with it and see how it goes, because I think that could be really helpful to you in this class as well as in other classes if you already hadn't worked with that. So moving forward, your turn-in work. Mr. Byers sent out an email last week asking us to have everything due on the day you would normally have class. So everything is going to be due on Wednesday, which is April 8th. So everything is due at 8 a.m. We're not going to have a staggered, have it due the next day, the classwork, and then have the homework. So everything's all due at one time. So you have 3 worksheets to be working on. You have the video questions from Ancient Chemistry, which hopefully you answered while we watched the video. We have the video questions for Ernest Rutherford, and you have this practice reading chemical formulas worksheet. The other thing for you guys to do is to fill out the survey. I hate to say this, but I need it before Wednesday, April 8th if I'm going to be able to talk about it when I'm making my video. So what I'm going to be doing is I'm going to be printing the responses that I've received at 4 p.m. on Tuesday so that I can finish videotaping the lesson for Wednesday. I know it's an awkward time, but that's probably about as late as I can do that, print them out, and then record the video, upload it to YouTube, upload it to Edpuzzle and all of that. So 4 p.m. on Tuesday. So if you could fill that out, I would greatly appreciate it. It's been very helpful to me. So regarding bookwork, it's due to time constraints at this point. I am going to try to minimize the amount of bookwork that you guys are doing in order to accommodate a slightly so we have less time than where you guys are spending on concepts. So what I would normally assign from 4.4 is section 4.4, which is on chemical formulas, and it would have those questions. And 4.5 has actually another description of Ernest Rutherford's experiment, his gold foil experiment. So if you feel like you need to do a little bit of reading or want a little extra practice, feel free to take a look at this. Your book is actually really good with this. This is actually one of the reasons I picked this textbook, because of all the books I was looking at, this was the only one that had you going through and counting the atoms back here. And I felt that that was really a good thing for you to do. So this is optional, not assigned. Looking ahead, math videos. I found out about a new app, and I'm going to be working on that and posting some of those out as some optional things for you guys to watch, with some information about your Chapter 2, Part 2 test. I'm currently working on emailing rubrics to individual students. I finished all the ones for your curation project, and I've got PDFs of them, but I've got to email them to all of you individually. So that's 48 emails. That's a lot. So just bear with me. I will get them to you. I'm doing the same thing with your test. So I will be emailing those to you also. Again, be patient. It takes a while to scan all those in and then email them. So I'm working on that. So one thing that we're going to be doing after spring break is building some models of elements. And you're going to need 3 different colors of something small. And the thing that I'm thinking is little candies like M&Ms. Probably like 25 to 30 of each. And you really want to keep them as 3 different colors. So you can use one color to represent protons, one to represent electrons, and one to represent neutrons. I'm thinking something that looks like mini M&Ms will work really well for protons and neutrons that would be in the nucleus, because they're going to be in a really small area. Larger ones are going to be okay for electrons. So as you guys are going through Easter time, and you guys hopefully will have something, think about putting some aside that you can work with. We're going to be doing a couple of things with them for you to do some hands-on models of some atoms, some isotopes, some ions, some other things, because I think that that will be really helpful to you, especially because I'm not in front of you and I can't show you some of the models and things that I would have in the classroom, which would be really helpful. So that's something you're going to need moving forward. So think about that as you go through the next 2 weeks. I think that's all I've got. So ladies, good luck with all of this. I hope that you were able to understand the videos and follow them, and that your work on the one worksheet is going okay. If you do have questions, put it into the survey. In addition, if you do need me to mail you the packets and the papers, please send me your street address. I don't necessarily have them. They might be correct in PowerSchool, but again, they might not be correct, and I don't really want to assume that they're fine. Some students have moved since the beginning of the school year. If you did send me your mailing address last week, I do have it, and I will send that out to you. So ladies, until next time, and good luck with your last couple of days of school before spring break. And I am looking forward to spring break probably as much as you guys are. So talk to you later.